So the first thing tonight is homework 8. That's going to be for Tuesday, the 24th. That's next Tuesday. So I picked 2 problems out of chapter 16. Those are dealing with your confidence intervals. All right? And then I picked 2 problems out of chapter 17. And these 2 are dealing with your test of significance. Now, that problem number 16.10 in chapter 16, you're going to calculate a couple different confidence intervals. It's all the same data, but what happens is, part A, you're going to start changing the confidence level to see how that changes the margin of error. And part B, you're going to change the sample size to see how you change the margin of error. 1625, you're just going to, here's the data. You'll have to calculate X bar, right? And then you'll calculate the confidence interval at whatever level they tell you. They ask you to make a graph here, and my suggestion that you make for this is a histogram out of Minitab. Okay? 1722 is a multiple choice question, and it's asking you something about, comparing your p-value to significance levels. And then 1741, that's a problem where you're going to work from start to finish. Test of significance. You're going to state the hypotheses, find your test statistic, find your p-value, then make your statement, right? What do we do here based off of what my p-value is, okay? So that's everything we've covered in those 2 chapters, to be honest with you. Now, before we finish chapter 17 and we move on to the next one, there's one other thing I want to point out to you here, all right? There's a connection between a 2-sided test, right? So the alternative is not equal to, right? Mu is not equal to something, and a confidence interval. Now, here's the deal, all right? The 2-sided test, the not equal to, is at level alpha. So there'll be a significance level there, right? Some percentage, like 1%, 5%, 10%, whatever it is, 0.01, 0.05, 0.10, yeah? That you would like to compare your p-value to say, if your p-value is less than alpha, then the data is significant. If your p-value is less than alpha, you want to reject H0 in favor of the alternative. You want to pick the alternative, right? Remember, you're comparing. If your p-value is bigger than or equal to alpha, then the data are not significant. Yes, you do not want to reject the null hypothesis. The data is consistent with the null being true. Yeah? Okay. What you really want to be able to do is you want to be able to do a 2-sided test. But the catch is the problem actually gives you a confidence interval. Right? So you've got a confidence interval. That is at the level. Now remember, every confidence interval you do, I've done, always has this confidence level we work at, whether it's 99%, 95%, 90%, whatever it is. Okay? The catch is that's the connection, right? That the confidence level is 1 minus your significance level. So if your significance level is 5%, the problem is showing you the confidence interval at the 95% confidence level. All I'm telling you is the confidence level of your interval and the significance level of your 2-sided test add to 1 or 100%, right? That's what I'm telling you there by saying that C is equal to 1 minus alpha. So my thought is this. You really want to do a 2-sided test. That means we're supposed to state hypothesis, calculate your test statistic, find your p-value, and state your conclusion, right? But you're given this. We can make a decision. We can tell you what to do by looking at the confidence interval. Now, where this shows up in your book, it doesn't show up in the middle of the chapter 17. It shows up as exercises at the end of chapter 17. This shows up in exercises. But I wanted to mention it because I'm going to use it on your capstone. Probably not Tuesday, but the next Tuesday. Okay? And it's problem 1744. These are not for you to turn in. This is where this is all explained to you. And then 1745. Now, I'm going to explain to you what you're going to look at and what you're doing here, because it's going to look confusing to you that all of a sudden somebody's wanting me to do a two-sided test, but they're giving me a confidence interval in the same problem. Normally that doesn't happen. Normally somebody doesn't ask you about, do you have evidence of something, and then give you a confidence interval in the same problem. It's either, here's the calculate the confidence interval, you're trying to estimate your parameter, or do the test of significance, and you're looking for evidence of this. But when they get put together, I want you to think about this. There's a connection between a two-sided test and a confidence interval. Look, is a two-sided test two-sided? Looking both ways, right? Is the confidence interval two-sided? Do you go both ways from your center, from your x-bar? Don't you add the margin of error and don't you subtract the margin? Hell, they're both two-sided, okay? Here's the way it works. This is the test I would like to do. Now, I'm taking all the numbers away and giving it to you in general. I know if I'm looking at a two-sided test that this has to be the case. Now, that little mu subscripted with a 0 could be any number, right? It depends on what the problem is saying. But a two-sided test, the hypotheses are set up like this. Okay? And we're using level, that's your significance level, alpha. You know I'm looking at the significance level when I write alpha. When I write capital C, you know I'm looking at the confidence interval. Okay? You'll be given a confidence interval at level so again, if alpha is 5%, the confidence interval will better be at the confidence level 95%. If you're looking at the 1% level for significance, your confidence interval will better be at 99%, right? They got to add to 1 or 100%. If this happens, all you need to do is this. You look at this value that's in the null hypothesis. One of two things is true about this. One, if mu sub naught is in the confidence interval, we do not reject the null. I'm going to give it to you in terms of symbols. We do not reject the null hypothesis. I didn't have to calculate the test statistic. I don't have to calculate the p-value. I didn't have to do any of that. It's just saying, okay, let me look. Here's your confidence interval. Here's your two-sided test. Take the value that's in the null. If it is in the interval, you're going to have an interval of numbers, right? If that value is in there, that mu is equal to, we do not reject the null hypothesis. 2, if the value in the null is not in the confidence interval, what do you think we do? We reject the null hypothesis. I don't have to calculate my little z-score. I don't have to find my p-value. I can tell you exactly what to do by where that little value that shows up in the null hypothesis falls. If it's in the interval, do not reject. Outside the interval, reject the null in favor of the alternative. That's all you have to do here. That's what they're explaining to you in this exercise 744. And then they're going a little example of that. You're working a problem here. And that's the same thing that's happening in 1745. Right? So what this does is it stops us from having to do the whole test. And I can base my conclusion about the two-sided test off of the confidence interval. I'm going to circle one more thing here. You've got to have that connection. 95 and 5 or 99 and 1 or 90 and 10%. You've got to have that connection there. Does anybody understand what just went on here? I don't have to do I don't have to do the test of significance. I don't have to calculate the z-score. You notice I don't even have to give you the x bar. Right? I don't have to give you the x bar. I don't have to give you anything. I don't have to give you the sample size or nothing. It's just, is that value in there or is it outside? Because here's the deal. Let's try this for a second. Let's say that this is your sampling distribution. Okay? And we get an x bar here. Okay? And just for the sake of things, when I form my confidence interval, it does that. There is one where when you calculated your confidence interval, the little mu here is not in there, right? Remember, that's what the null hypothesis is making a statement about is, where is that sampling distribution centered? What is that value of mu? Yeah? If your x bar is so far out the tail that the confidence interval at the appropriate confidence level does not capture the center there, what does that mean? This is when you reject H naught. The reason is, based off of what I see here, your p-value is going to be less than your alpha. In other words, that x bar is far enough out the tail that when you calculated the confidence interval, the little value in the null hypothesis is not in there. Your x bar is far enough out the tail that your p-value will be less than your significance level, and we want to reject the null in favor of the alternative. Another possible thing could happen here. Okay? The same sampling distribution that we're given. Here sits your mu, and then your x bar is right here. And then when you calculated the confidence interval, mu is in there. Here, you fail to reject H naught. In other words, your p-value will be bigger than or equal to your alpha. Your x bar is not very far out the tail if when you calculated the confidence interval, the center is in there. The value that's in the null hypothesis. This is what's going on here. Yeah, I know. I'm drawing you pictures. I'm drawing you pictures of these two statements here. This is number 2 back there, and that's number 1. That's what went on. So you don't have to worry about calculating your test statistic, calculating your p-value, any of that stuff. I can just look at the value that's in the null. It's either in there, in the confidence interval, or it's not, and I can make a decision. I can tell you exactly what I want to do there. Look, the way this works, turn to page 414, and there's a 1745. It says test from confidence intervals. It's a question about this. Look, I want you to think about this as when they're asking you to do a two-sided test, and all of a sudden the confidence interval shows up in the same problem. Think about what we've just talked about. It says a 95% confidence interval for a population mean is 30.7. So this is 1745 here. The confidence level is 95%, right? Your C is 95%. It is 30.7 plus or minus 3.2, right? So your x bar must be 30.7. Your margin of error is 3.2. You're going to add it and subtract it and get the 95% confidence interval for this population mean. It says, use the method described in 1714 to answer these questions. No, use the method I just talked about here, right? This is what I just talked about, this connection between a two-sided test and a confidence interval. Part A says, with a two-sided alternative, can you reject the null hypothesis that mu is equal to 33 at the 5% level? Does everybody understand why they're asking me at the 5% level? My confidence interval is at the 95% level. 95%, 5% is 100%. In Part A, what they're asking you to do is this test right here. Mu is equal to 33. It says two-sided, so the alternative is mu does not equal 33. So you take this value right here, that mu is equal to 33. Then the question is, this interval here from 30.7 plus or minus 3.2, is 33 in there? $33 is in 30.7 plus or minus 3.2. It's in the interval. And what did I tell you to do if that's in the interval? We do not reject H naught at level alpha equals 5%. I didn't calculate any test statistic. Hell, I didn't find any p-value. I didn't use table A in the back of the book. I just know if it's in the interval, your X bar is not very far away from it. And then you go to Part B. Now, Part B has to be the flipped side to this, right? Part B says, with a two-sided alternative, can you reject the null hypothesis that mu is equal to 34 at the 5% level? So Part B, they're doing this test of significance. What did they do it to? Was it 34? 34. The alternative is mu does not equal 34. Now, your confidence interval is still the same. It's still 30.7 plus or minus 3.2. Right? And again, your alpha here is still the 5% level because the confidence interval is at the 95% level. Okay? Now, is 34 in the interval or not? I got a couple head no's. 34 is not in 30.7 plus or minus 3.2. And as soon as it's not in that interval, then your X bar was far enough away that we want to reject the null hypothesis. We reject H naught at the 5%, alpha equals 5% level. Now, you realize if we reject H naught, then we're willing to accept the alternative, right? We're getting rid of the null and in favor of... Look, when you fail to reject the null, you just fail to reject the null. When you reject it, you've got to accept something, so you're willing to accept the alternative, right? So you're willing to accept that it's not 34 here. I didn't calculate any test statistics on either one of these. I didn't calculate p-values. I didn't use table A. I looked at the value in the null hypothesis. Is it in the interval or is it not? If it's in there, you fail to reject the null. Your p-value will end up being bigger than or equal to your significance level. If it's not in there, like Part B, 34 is not in there, we want to reject the null at that level, and we want to favor the alternative. That's all there is to it, right? Look, you got to have a note here that if I gave you a problem like this, you'd come back and tell me, dude, what the hell are you doing, man? I don't have any sample size. How do you want me to do a two-sided test without a sample size, a test statistic, and a p-value? You want to think about this connection anytime there's a two-sided test and, dude, you threw a confidence interval in the same problem? This is the connection here. This is how you attack this. You don't have to do anything. You just look and see. All right? Now, chapter 18. I need a favor from you folks. I don't ask a lot from you. Well, not out loud. I need you to read chapter 19 because there's only going to be a few things I talk about in here. I'd like for you to read the rest of it. I never told you to read anything. I never asked you to read anything. there's certain things I want to talk about here because it's chapter 18. The title of it is Inference and Practice. So it's some things that we need to be aware of. Okay? So again, I'm going to talk about what I want to talk about, and I expect you to go back and read the rest of it. All right? Now, at this moment here, you've done 16 and 17. There's two procedures. And when I say procedures, there's two statistical inference methods that we have. One is a confidence interval, and the other one is a test of significance. The confidence interval is used to estimate a population parameter. The test of significance is to assess evidence about claims for a population parameter, right? That's what we're doing here. Do you remember there were simple conditions? Simple random sample. I'm going to remind you those. I'm reminding you of what we've done here. I had simple conditions through the last two chapters. The first one was you had to have a simple random sample. And I'm going to be honest with you. If you looked at any problems or any of the problems I've done, it's been a random sample where we're going to assume that it's as good as a simple random sample if it doesn't say SRS. 2, the population distribution, where you're drawing your sample, where we're looking at the value of the variable amongst all individuals in the population is always got to be normal. And then the only thing I'm going to write for 3 this time is sigma is given. And I'm going to underline that. That's how I know that I am using these two statistical inference methods. The one from 16 for a confidence interval, the one for 17 for a test of significance. In all the problems, we're dealing with a population mean. What we're calculating from our sample for our statistic is an X bar, and in every problem, sigma is given to you. Okay? Now, the two procedures have a name. Are called Z procedures. The reason they are called Z procedures is because your confidence interval uses a critical value. You remember the formula? There's a little Z star in there that we go back to table C and we look up how many standard deviations on each side do we need to go to get 95%, 99%, 90%, right? So there's a Z-score that shows up in your confidence interval. Obviously, we write little Z star, right, for this being special. It's a critical value. Depending on your confidence level, on how many standard deviations on either side you go, it uses a Z-score. The test of significance. What the hell is your test statistic there? Didn't we calculate Z-scores on Tuesday? It uses a Z-score to start finding your p-value. It uses the Z-score as your test of significance. That's the reason they're called Z procedures. Now look, I know that don't mean shit to you now. That all of a sudden I got these two and I give them a name because we only know 2. Give me next Tuesday. You're going to see something that are no longer Z procedures, right? They don't use Z-scores. Now this is all we got. It would be nice to know that, when sigma is given to me, we're trying to deal with a population mean, that we use Z procedures. Both the procedures have a Z-score in them. Now, here's the thing. On page 416, 417, 418, 419, 420, 421. This is all about what you need to be cautioned about, right? So I'm going to do it like this. Pages, what did I say it was? 416 to 421. These are little things you need to be aware of, right? It says conditions for inference and practice. Where did the data... I'm just reading the little highlights here that you're going to go through and read. It says where the data come from matters. Do you think it does? In other words, how our data got produced. Where did our sample come from? You think it makes a difference how we chose it? If it doesn't, why in the hell every time I write down those simple conditions do I write down our stuff's good for an SRS? Yeah, it matters. You think it matters if it comes from a convenience sampling or a voluntary response? You're going to trust the results of a confidence interval when you saw convenience sampling used? No. You're going to trust the results of a confidence interval when you see that the data came from a voluntary response? You're going to trust it? No. We only trust it if it's a simple random sample or something that was a random sample. Right? That's what our methods are good for. That falls through for a confidence interval or a test of significance. Does it matter? Yeah, it matters. Here's my thing. You ever heard the term crap in, crap out? No? The hell, I'm old. Well, probably not the word crap gets used. You know, when you put bad stuff in, you get bad stuff out. If you put bad data in, these inference methods don't fix the bad data. Oh, yeah, I understand that the confidence interval comes with a margin of error, right? That tells you how accurate we believe our estimate is. That margin of error doesn't tell you anything about undercoverage, non-response, biased survey, nothing. That's not there. That margin of error is there because we use chance to choose the sample, and we know we're not exactly right. It doesn't make up for bad data. So if I can get you one thing here is if you got bad data and you think you're going to calculate a confidence interval or do a test of significance, you might just wad that shit up and throw it in the garbage. It ain't no good. The p-value is not going to be accurate. Hell, the confidence interval is not going to be any good. Okay? Let me ask you this. Suppose you got an outlier in your data. How does that mess things up? What does it do? Remember, the X bar is used in the confidence interval and the test of significance. What's the outlier? Let's say the outlier is on the low side. What does that do to X bar? It pulls X bar this way, right? Yeah? You think one outlier can make a difference in your confidence interval? It's going to pick it up and it's going to move your X bar, right? It's going to move the center. You going to trust that confidence interval? No. What do you think an outlier, let's say, you're doing a test of significance and you're looking to the left. Your outlier's to the left. So it's pulled the X bar to the left smaller. You understand that's going to produce a smaller p-value than we would have had without it, right? It can make something be significant that is not. The one outlier could. An outlier can screw things up here too. See number 2, the population distribution is normal. That means there's no outliers there, right? It's roughly symmetric. The shape and all that makes a difference or we wouldn't be telling you that. Okay? Number 3. Yeah, that's what these cautions and things are on these 416 to 421. It's reminding you of this. Why are these important? You can't do anything with what happened in chapter 16 and 17 unless sigma is given to you. How do I know that? Hell, sigma shows up in the confidence interval. Sigma shows up when you calculate your z-score. If you don't have it, you can't do it. Right? So you have to be given that. Now, you're going to read, right? Because there's one other, we do one other screwed up thing here. And when I say screwed up is, you understand we're in the classroom, right? We're not in the real world. Agreed? So one of the things that we do with test of significance is a little filed up here. Is I'm thinking about test of significance. And I've got a significance level of 0.05. And my p-value comes back to be, so I've done a test. I'm doing it at significance level 5%. So I'm looking at the 0.05 level. My p-value comes back to be 0.049. What do we do in this class? Your p-value is less than alpha, right? 0.049 is less than 0.05. What do? You reject the null in favor of the alternative, yeah? The data is significant at level alpha is equal to 5%, yeah? Because, in case you don't know, my p-value is less than alpha. Reject the null. The data is significant. But you know what's screwed up in this class? Suppose you got a p-value of 0.051. What do we say now in this class? Oh, no. Son, your p-value is bigger than or equal to your alpha. The data is not significant. You don't want to reject the null. I was getting ready to call you all dudes. Hey, is there really any difference between 0.049 and 0.051? Yes, there is. It's 2 what? That's 10. That's 2 1,000ths. Changing by 2 1,000ths, all of a sudden something was significant and now it's not. Now you want to reject H0 and now you don't. Now you understand we have to do that in this class. Yeah? because you got to give me the answer. Oh no, if you're less than it, boom, reject H naught, the data is significant. If you're bigger than that, don't reject H naught, no, you're not significant. In the real world, is there any difference here? In practice? No, you're going to tell your boss, dude, I don't know, man. Things are too close to call here. And I'm going too close to call here either way. Let me put it to you this way. Let's say you work for a company that, has got some machine that makes something. We're manufacturing a product. Let's say just for the sake of things, we're manufacturing ball bearings. All right? And they have to have a certain diameter. Let's say the diameter needs to be 5 centimeters because you sell them to somebody and they won't take them unless they're 5 centimeters. Now, you understand there's a little plus or minus something going on here, right? They're not all going to be exact. But your boss wants you to go out and see if the machine's doing what it's supposed to do. So you take a sample. Yep. And all of a sudden, when you take your sample and you calculate what the diameters are of your sample, random sample, 1,000 ball bearings, you get a p-value of 0.049. You go back and tell your boss, yeah, there's something wrong with the machine. We need to replace it. Now, the machine costs $5 million. You know what's going to happen if you go back and tell your boss that and you show him all this shit? The next time you're working somewhere, in your next job, you won't tell your boss that. You'll say, look, it was too close to call. What about if you got a p-value of 0.051? You're going to go in and tell the boss, all's clear? The next shipment you say might come back. So the next time your new boss asks you to do that, you'll tell him, look, that's too close to call. Usually students remember things when I start attaching money to it and jobs. You're not going to put your job on the line here either way, right? You're going to tell him, look, we need to let it run a little bit. We'll take another sample and we'll see what we get. This is too close to call. In the real world, I can't tell you that the machine, is not making them at 5 centimeters or it is making them at 5 centimeters. I can't tell you that. Because 0.049 and 0.051 in the real world, being off by 2 1,000ths, hell, the government don't even work that close. Right? Your engineering stuff, 2 1,000ths, we're in good shape, ain't we? Depends on what we're looking at. If I'm looking at $3 million, 2 1,000ths, close enough. Not to make a call. Okay? I wanted to throw that one out there to you because that's one of the things that they're talking about here. My other thought is this. Now, this is actually something I did really want to talk about. And there's 2 things here. There's something called statistical significance, which is what we're talking about. Versus practical significance. Now, the first thing is statistical inference comes from a test, right? It comes from a test of significance. Whether the data are significant at this level or whether it's not. Practical significance is, look, is there anything in the real world here that actually matters? Okay? Now, when to pay attention to this? This becomes an issue when the sample size is very large. I mean like 10,000, 20,000. I'm talking like a large sample, or very small. I mean like you took a sample of size 2 or size 3. Look, this whole story here, statistical significance versus practical significance. When the sample size is very large, this becomes a concern. And when the sample size is very small, this becomes a concern and something to pay attention to. All right? Because all this deals with is remember, that's the standard deviation of your sampling distribution, sigma over the square root of n. Does everybody understand that the larger that n is, the smaller that number becomes? Right? The smaller that number is, the larger this thing becomes. Yeah? So here's the problem. When your sample size is very large, let's say it's like 10,000, 50,000 in your sample. All right? I'm going to write it down for you. When n is large. 10,000, 20,000, 50,000. When it's large, sigma over the square root of n is small. And I'm going to put the word very here and very here. So the problem is when your sample size is very large, 10,000, 20,000, 50,000, that standard deviation becomes very small, like 0.001, 0.001, 0.0001, very small, in decimals, right? Well, the problem is, if that standard deviation is very small, how far away do I need to be 3 away? I don't have to be very far, right? In other words, if that standard deviation turns out to be 0.001, because your sample size was so large, you made that standard deviation all the way down to 0.001. How many is 3 standard deviations? It's 0.003. Yeah? It's 0.003 to the right. It's 0.003 to the left. My point is this. If your standard deviation is 0.001, you got to be bigger than 0.003 to be more than 3 away, to get a small p-value, to want to reject the null hypothesis, for your test to tell you that you are statistically significant. Being off by 0.003, is there any practical significance in most things? And the answer is no. So what's going to happen in this case, when your sample size is very large, that standard deviation is very small because you're dividing by a very large number, you are going to see the test is going to tell you statistically significant. It's going to pick up any minor x bar. Hell, x bar is only got to be 0.003 away. Anything just a little bit away on either side is going to be statistically significant, right? So the test is going to tell you statistically significant. The problem is no practical significance. Okay, so you're off by 0.004. You're off by 4 1,000ths. The larger you make that sample size, the smaller that standard deviation gets. Here's what I'm doing. You know the null hypothesis is mu is equal to something, right? Where this distribution is centered. It's centered right here. The smaller you make that standard deviation, you don't have to be very far away to be more than 3 away. Well, the test is immediately going, any difference for your x bar from here out or from here out is going to become back as statistically significant. Hell, you only got to be 0.003 away on either side to be more than 3 away. The test is going to say, big flag, statistically significant. Then you look at your little x bar, and your x bar is off by 0.004 from your mean. 4 1,000ths? There's no practical significance. Now, one more time. This becomes a concern when the sample size is very large. The test is going to pick up almost any difference as being statistically significant. The problem is there's not going to be any practical significance in that. The flip side to this is if you're, how did I write that one? When n is very small, like 2, 3, 4, something like that. Sigma over the square root of n can still be rather large. So here, if that standard deviation, sigma over the square root of n, I mean, it depends on what sigma is. And if your standard deviation, if you're looking at samples of size 2, 3, or 4, you didn't cut it down by much. So that standard deviation can still be large. It might be like this. So for me to be 3 away, do I have to be a long way away? Yeah. All right, I got to be a long way out the tail. If that standard deviation is large, I got to be a long way away from the center. The problem is, if it's this large and I go 3 away, I have to be way out here. The problem is this right here actually might make a difference. So what happens when the standard deviation, when the sample size is small, 2, 3, or 4, that standard deviation can still be large. So what happens is the test tells you not statistically significant. But the standard deviation was so large, the test didn't pick up the practical significance of things. That you are actually, in the big scheme of things, far enough away to be important from the center. So the test is going to tell you nothing. Dude, look, your sample size was too small. The standard deviation is still too large. You've got to be so far out the tail one way or the other to be statistically significant. The test ain't going to pick up nothing as being statistically significant. The problem is you do have practical significance. Now, I always thought all this was a bunch of crap. I teach the class. I still thought it was a bunch of crap. Right? That people actually paid attention to this. So one day I'm watching TV and there's a dude, I can't remember which news channel he was on. He was out of Toronto. And he was studying cell phone use of brain cancer. Now, I don't make my stories up. At least that you'll know. Okay? So this guy was on TV, he's talking. He was doing a study, right? He was doing an experiment about cancer and cell phone use, whether it causes cancer. And so what he did was, he was reporting his results. That wasn't the shocking thing. His results was, they did like a sample of 1,000 people. And he didn't find any statistically significant results. That seemed reasonable, right? In other words, there was no connection between the cell phone use and brain cancer. And the dude should have quit talking at that point. Because the next words out of his mouth was, look, we're going to keep taking larger and larger samples because I know at some point we'll get some statistically significant results. Dude, you mentioned that was on TV. You said that. What's he talking about? He knows if he keeps increasing his sample size, this is the first one, right? That the test will come back statistically significant even if there is no practical significance because you've made that standard deviation so small, it'll pick up any minor difference as statistically significant. Yeah, the dude said that. Oh, no, we'll just keep taking a larger and larger sample. And I know that we'll eventually get statistically significant results. Okay. So the sample size kind of does play a role, right? When it's very small or it's very large. You get these little problems. The test will either come back and tell you it's statistically significant, there's no practical, that's the large one. Or the test will come back and tell you no statistical significance, but there is a practical significance. That's where the sample size is very small. Okay? Now, the two other things I want to do here. I'm on page 424. I'm going to try to make this as simple as possible before we ever do anything. We have the opportunity about choosing the sample size. This is where we're going to do a confidence interval. Okay? Here's what we're going to do. We're going to fix a confidence level. In other words, we know what confidence level we want to use, whether it's 90, 95, that we can work with, right? Whatever it is. And a margin of error. So we know what confidence level we want to do the confidence interval at. We know the margin of error that we can live with at the end. In other words, we know what we can live with on how wide our interval is. Based off of fixing the confidence level and the margin of error, then I can tell you what size sample that we need. So what we're going to do is this. I'm going to do this like this. We know the margin of error is this. Z star sigma over the square root of n. Go back and look at your confidence interval. That's the margin of error. It's x bar plus or minus that part. Now, I'm not going to do the algebra here, but if we solve for the sample size, we're going to get n is equal to z star over sigma divided by m squared. The Z star comes from the confidence level. The margin of error will be given to us. The sigma comes from the problem. So if we know the confidence level we want to work at, we know the margin of error that we can live with, then we can choose the sample size that will deliver this for us. Now, what's the problem with this? Remember, it's that time and money on how big a sample we can work with. So if things are reasonable, this will be what we do here. Now, here's what I want to do. I want to come down here and I want to look and see what kind of problems I got here. And I'm on the bottom of page 425. I don't want to do the example. Hell, it's there for you to look at. Let's look at 18.12. Okay? See how this works. And then how do I know I'm choosing the sample size? What's the wording of the question? It says, example 16.1 on page 375, assume that the body mass index, BMI, of all American young women follows a normal distribution with a standard deviation sigma equals 7.5. Okay. So my important part is that sigma is 7.5. Remember, the standard deviation had to be given to me. It says how large a sample would be needed to estimate the mean BMI mu in this population to within plus or minus 1. You see the plus or minus part? That's the margin of error with 95% confidence. So the question is, you need to find n where your margin of error is plus or minus 1, and the confidence level is 95%. It says how large a sample would be needed. It wants you to find the sample size for that confidence level and that margin of error. Okay? So immediately I'm running to my formula sheets. On your formula sheets, there's one that says something about choosing the sample size given sigma. There it is. It's looking at you. So what we do is we pull it out and say, look, this is my guy here, Z star times sigma over m. Please do not forget that little squaring part, because I guarantee you, if you do, the answer without it being squared is there. It makes for an easy wrong answer. Okay? Now, what is Z star? When the confidence level is 95%, you go to table C in the back of the book, you find 95% confidence, you read down till you find Z, you will find Z star equals 1.96. You plug that in. N is equal to 1.96. I'm going to put a little times there. We're multiplying. Standard deviation was given to me of 7.5. Okay. Now, look. I wrote this like this for you up here. This margin of error being plus or minus 1. I wanted you to know wherever the plus or minus part is, that's your margin of error and your confidence interval, right? It's your estimate plus or minus your margin of error. The plus or minus is just telling you you're going to add it and you're going to subtract it. The margin of error here is, remember, you add the margin of error and you subtract it. The margin of error, you don't have to worry about the plus or minus. I wrote that so you knew that was the margin of error. The margin of error here is 1. And then you're going to square that. So we're going to get n is equal to whatever in the hell 1.96 times 7.5 squared is.
Are you squaring 7.5 or are you squaring out?
All of it. Everything. So the question he's asked me is what am I squaring here? So I'm squaring everything that's on the inside, right? So I'm going to take the 1.96 times the 7.5, get an answer, and then we're going to square that. Marcus? 216.01. Now, here's the thing. That's exact, right? When you did all that calculation, the 1.96 times 7.5 divided by 1, squaring it, you got 216.01. Now, I can't take a 0.01 of a person. I can't take a 0.01 of anything where I'm taking a sample. Now, since we're doing the sample size here, we always round up. So what we're going to do here is we're going to take n equals 217. Don't chop those pieces off. Don't make that 216. Here's the reason why. If we always round up, See, we're using a little bit larger sample size than we needed, right? We went to the next whole number up. Even at 0.01, I went to 217. Because when you actually calculate the confidence interval with the given confidence level, your margin of error will be a little bit smaller than what was asked to happen, that everybody's happy. If you use 216 at that confidence level, your margin of error will be a little bit bigger. And that's what we were not asked to do. We'll take the margin of error being exact or a little bit smaller. We don't want to be bigger, so we always round up. 216.01 goes to 217. If that was 216.001, that goes to 217. We always go to the next whole number up. Okay? Now look, 1813 is done the exact same way. If they're asking you to choose a sample size, they've got to give you sigma in the problem, they've got to give you the confidence level, and they've got to give you the margin of error. If you look at 813, number skills of 8th graders. I'm not going to do it. I want to point it out to you. It says, suppose that scores on the mathematics part of the National Assessment of Educational Progress, NAEP, test for 8th graders follow a normal distribution with a standard deviation of 125. There's your two, right? There's your two conditions. They're not going to say an SRS. You're getting ready to choose an SRS, right? It says you want to estimate the mean score within plus or minus 10 with 90% confidence. What's the confidence level? 90%. What's the margin of error here? Plus or minus 10. The margin of error is actually 10. Yep. The Z star for 90% is 1.645, and you'll just plug in and make sure. Can I scream at you about this one more time? Don't forget that little squaring. And you're squaring everything inside the parentheses. All right? Now, when you read, remember I asked you to read this chapter, right? On page 426, there's an 18.5 Plan and Studies, the power of a statistical test. Don't read that. Please. I'm going to page 429. You won't be happy if you read the power of a test. There's a reason why it has a little star there. It's starred, so we'll skip it. Okay? Well, it's starred, so I'm going to skip it. The last thing in this section, okay, is something called type 1 and type 2 errors. Now, here's what we're going to do. This is where we use a test of significance, to make a decision. At significance level alpha. When we're forced to make a decision, and what I mean is, look, we've already been to the point where you reject the null and you accept the alternative as being true, right? We've already done that one. But, when you fail to reject the null, that's all we ever said, right? We fail to reject the null, the data is not statistically significant, the data is consistent with H not being true. We never actually told you that the null hypothesis was true. Well, when somebody's going to force you to make the decision between the null and the alternative, we will actually let you choose the null as being the truth about the population. That mu is equal to whatever value it is. That's the only time we allow that. Now, here's the deal. There's two pieces here we're going to do. We're going to accept the null. This is whenever your p is bigger than or equal to alpha. I would have never allowed you to do that before. I would tell you, we fail to reject the null. The data are consistent with the null being true. But if you're going to make me choose, if you're going to make me make a decision when your p-value is bigger than or equal to your significance value, your significance level. In other words, we didn't find anything. The data is not significant. We will accept the null as being true. I never allowed you to do that one before. Only when somebody's going to force me to make a decision. Choose one based off the test. 2 is we reject the null and accept the alternative. Now, we've allowed us to do this. We've done this already. This is when your p-value is less than alpha. We've done that all along, right? You want to reject the null in favor of the alternative. You're trying to pick the alternative here. The problem is when we do this, based off a test of significance, you pick one or the other, we make errors, right? You make errors. In other words, you make incorrect decisions about what is true and what is not. You make two errors. There's two possible errors that can be made here. One is what's called a type 1 error, statistician's language. I'm going to give you some language of medical testing. They don't talk about type 1 and type 2. They talk about false positives and false negatives. Okay? A type 1 error is you reject H naught, right? That's based off the test. When H naught is true. Okay, so I'm going to do it like this. The test is telling you to do this. So whatever happened, whatever X bar you had, the test come back and told you that you should reject the null hypothesis, that you should accept the alternative. You got a p-value smaller than your significance level. The problem is the test was wrong. And the truth about the population is H naught is true. That's about the population. That's the truth. That's what's really happening here is the null is actually true. Mu is equal to whatever it is. A type 2 error, okay, is you accept the null. The test is telling you to do this. So your p-value was bigger than or equal to alpha in your test, right? That's what it told you to do. Accept the null. But the problem is when the alternative is true. And again, this is the truth about your population. These are both incorrect decisions. If you're going to reject the null when the null is true, that's not correct. If you're going to accept the null when the alternative is true, that's not correct either. All right? Now, I got one other thing here before I do a little more with this, all right? Somebody might ask you, what's the probability of a type 1 error? In other words, what's the probability that you reject H naught when H naught is true? It's very simple. The probability of a type 1 error is whatever your significance level is. There's nothing to be calculated. You're doing all this test significance. Somebody's giving you a significance level, the 1%, the 5%, the 10%, whatever in the hell it is. The probability that you make a type 1 error is exactly the significance level that you are using to make your decision. Nobody's going to ask you about the probability of a type 2 error because it's not that clean. Probability of a type 1 error, okay, it's just whatever the significance level you're working at. 1%, 5, 10, whatever. Okay? Now, here's what I'm thinking here. I was going to draw you a picture of this. So, the way I think about these tests and making decisions, okay? Up here is the truth about the population. One of two things is true. Either H naught is true or the alternative is true. Over here is the decision we're going to make based on the sample, right, that the test uses. Well, you're going to do one of two things. You're either going to reject the null or you're going to accept it. Now, I'm going to write something here in blue underneath. When you reject the null, that means you accept the alternative, right? Everything is, look, in this textbook, and every time somebody tells you anything about test of significance, it's always in what do you do about the null hypothesis, because you assume that to be true to get the test started, so you either reject it or accept it. When you reject it, you're accepting the alternative. Okay? Now, if you reject the null, if you accept the alternative when the null is true, this right here, this little box here, that little intersection there, that's a type 1 error. Right? Remember? We rejected H naught. We accepted the alternative when the truth about the population is the null is true. Over here is a correct decision. We're hoping that we reject the null, accept the alternative when the alternative is true. That's a correct decision. Down here, you accept the null based off of your sample, off your test, when the null is true. That's correct. This is a type 2 error over here. You accept the null based off your test, off of your sample. When the alternative is true, that's no good. That's a type 2 error. Now, I got 2 that I'm going to do here. Right? There's probably a couple here we could look at. But I'm going to do it like this. I got 2 things actually to think about here. One is this. The jury trial. The jury trial makes errors, right? I was trying to think of the most recent one when they made an error, and I can't come up with one because I kind of quit watching the news and reading the news and stuff. So, the jury trial starts out with the null hypothesis is the person is, right? The judge says the defendant's innocent until proven guilty, right? And the alternative is the person is guilty. So now, if we send an innocent person home or we send a guilty person to jail, those are the correct decisions based off the test. What's a type 1 error here in the language of innocent and guilty? Type 1. You reject H naught when H naught is true. What did you just do? You just sent an innocent person to jail, didn't we? You said an innocent person is guilty. You rejected H naught, the fact that the person was innocent, and you accepted the alternative, that the person was guilty, when the truth is the person was actually innocent. You said innocent is guilty. What's a type 2 error? Well, that's when you accept the null when the alternative is true. What did you just do now? You just sent a guilty person home. You said guilty is not guilty. I have a hard time using that word innocent at that point. Now, sometimes your book will ask you in problems, I've never seen it on a test, is one of these worse than the other? Well, that comes with a little, it depends on what side of the fence I'm on. If I'm the person on trial, I'm thinking type 1's worse. Agreed? Yeah. If I'm the person that lives next to the mass murderer, I'm thinking the type 2's worse. So it depends on your perspective here on which one's worse. Neither one of them's good, but, in this case, I can't say. If I'm on trial, like I said, I'm thinking type 1's worse. If I live next to the guy or girl or defendant and they actually did it, I'm thinking type 2's worse. There's one other place this happens that I can give you like standard language without all the muse and all that kind of stuff. Medical testing. Now, the way I always set it up is the null. We go into this thought with the person being healthy. You need to be careful if you see something about medical testing. Is the null is the person has the disease or is the person healthy? Because then the errors will change, right? I always set it up as the null is the person's healthy. And The alternative is has whatever the disease is you're testing for. Whatever it is. Now, we make errors in medical testing. Actually, we looked at some back when we were talking about probability, and I was giving you a little story about HIV, and the little girl stood in the back of the room and told me, yeah, I've been tested, I come positive. Yeah. Remember that? So what's a type 1 error here? What does it mean? Look, on the final. That's the only place you're going to see this, unless there's something in the learning curve that asks you about type 1 and type 2 errors, is I would expect if there's a type 1 or type 2 question on the final, that you'd write the definition in the margin or somewhere, have it written down, okay, type 1 is we rejected H naught when H naught is true. And then you got to take the wording of the problem and put it in the context, right? You got to put that in there. What the hell does that mean to reject H naught when H naught is true? So what did you just do here? You rejected H naught when H naught is true. So that means you accepted the alternative, right? You just told a person has the disease based off the test that is healthy. Now look, medical tests, and they don't use no type 1, type 2 errors. What's this called? This is a false positive, right? The test comes back positive, but the problem was, that person was, that is healthy. What's a type 2 error here? What's it mean to accept the null when the alternative is true? Well, person is healthy by the test, but they have the disease. What's this? This is a false negative, right? The test is coming back negative. This says the person is healthy. But the problem is the truth about the person is they actually have the disease, right? They talk about false positive and false. How come we never talk about a true positive and a true negative? Those are the correct decisions, right? They always talk about false positive and false negative. Question here is, just like with the jury trial, is one of these worse than the other? Again, it kind of depends on which side of the fence I'm sitting on. See, a type 1 error, the person has a disease that is healthy. What happens to that person? We stick their ass in the hospital, we poke them another couple hundred times, and we eventually find out they're healthy, right? So if you're the person being stuck in the hospital and being poked another 1,000 times, that's probably not too good. What about the type 2 error? Is that one a bad one? Well, it depends on if I live next to the person that's got the plague or something. What happens to them? The test come back and said they're positive. We send their ass home. We don't have to test them no more. Yeah? Again, it's a matter of perspective on which side of the fence you're sitting on here, whether you're the person involved or whether you're the person on the outside looking. I always mention this because they mention this right in the middle of all this. Oh, this one's worse. No. Depends on who in the hell you are and which side of this you're on. All right? So, look, those are the kinds with, medical testing, jury trial, so on and so forth. That's the stuff I wanted to talk about in Chapter 18. All right? You're going to read. Don't read about the power of the test. You're not going to see me say anything about that. Now, what we're going to do is, all right, is I know I'm supposed to go to the next chapter, but I'm going to skip over a couple. And the reason I'm going to do that is there's only one chapter left where we're going to hand calculate. And what I mean by hand calculate is, we sit there and we calculate the confidence interval. We calculate the test statistic. We find the p-value and all that we do by hand. The last 3 chapters we're going to do is all going to be done on the software. So what that means is you need to be really good at reading the printout and interpreting. No hand calculations. So that's what we're going to work on in the last 3. The last chapter we do the handwork is this chapter 22. And we're going to do a couple things here. Not only is this the last chapter that we do the handwork, but this chapter 22, we do something else to you. It's inference, confidence intervals, and tests of significance about a population proportion. Okay. We're changing our population parameter. It's no longer a mean, mu. It's going to be the proportion of some outcome. Some proportion out of the population we want to estimate or make claims about. Okay? Can we take a look at example 22.1 on the bottom of page 517? It says, how common is behavior that puts people at risk of AIDS? In the early 1990s, the landmark National AIDS Behavioral Survey interviewed a random sample of 2,673 adult heterosexuals. Random sample, right? That's what we're looking for here. Of these, 170 had more than one sexual partner in the past year. That is 6.36% of the sample. Based on these data, what can we say about the percent of all adult heterosexuals who have multiple partners? We want to estimate a single population proportion. That is this chapter. We're interested in population proportion here. I'm not going to look at 22.2 because we're not interested in a single proportion there. So here's what I'm thinking. There's something called the sample proportion, and it's denoted P hat. Right? That's read as P hat. That's the proportion from your sample. Now, the parameter that we're interested in this chapter is what we're going to think about as the unknown. Remember, parameters are usually unknown for us. Unknown population proportion. It's denoted by P. So this is your parameter now. Your parameter is no longer a mu, not the mean. Your parameter is P. It's a population proportion. Your sample proportion, P hat, that's going to be your statistic. Now look, here's the way you want to think about this. When somebody's talking to you about, well, we want to talk about this proportion of the population, call the outcome whatever proportion you're looking for, call the outcome we are looking for we can just think about as being a success. If it's not a success, then it's a failure. Right? Whatever the outcome is you're looking at, whatever proportion you're looking for, we're going to call that a success. Okay? So, in this example that we were looking at here about adult heterosexuals, my example had this. P, your parameter. This was the proportion of adult heterosexuals with more than one partner. This is your parameter. This is the unknown quantity we would like to estimate. That's your parameter. Your parameter now is a P, a proportion of the population. In this case, a proportion of adult heterosexuals with more than one partner. Well, what are we going to calculate from our sample? That's going to be your sample proportion. If you remember, we had a random sample of 2673. And we had 170 that said yes, that they had more than one partner. That would be a success. If they had more than one partner, that would be a success. Yeah, I don't get all caught up on what the hell I'm treating as a success or what I'm not. It's whatever I'm looking for, that's going to be a success. If we're looking for more than one partner, that would be the success here, right? So there's 170 that said Yes. Again, this is the success. Our statistic this time is what's called the sample proportion. Just like we have a population proportion, the proportion from the population, we have a sample proportion, the proportion from your sample. Just like you had population mean, sample mean previously, we put the little sample population so you know what we're looking at. The sample proportion is your p hat. It's always the number of successes in the sample divided by the sample size n. So in our case, there's no magic about where they got that sample proportion in example 22.1. P hat was, you had 170 that said yes, that we're considering them as successes, and we had a sample size of 2673, and we got a proportion of 0.0636. Nobody wants to read the proportion as 0.0636. We move the decimal place and we get 6.36% of your sample had more than one partner in the past year. Now, here, this is always our statistic. Your sample proportion, the proportion of successes in your sample, where you take the number of successes in your sample divided by your sample size to calculate that sample proportion, that is your statistic. And just as we always do here, we want to use p hat to estimate You've got to have that little thought in your notes all over the place. We always use our statistic. We always use what we calculate from our sample to estimate the unknown quantity that we want to know about our population. You're looking at proportions. Okay, instead of writing p hat, write x bar. Instead of writing p, write mu. I wanted to use x bar to estimate mu, right? I want to use the sample mean to estimate the population mean. I'm not talking about means. We're talking about proportions. I want to use p hat to estimate p. I want to use my sample proportion, the proportion of successes in your sample to estimate the proportion of successes in my population. Okay? Now, just like before, that is your statistic, that p hat. It has a sampling distribution. The sampling distribution of this statistic, of p hat. What we know is this. We know the sampling distribution of that p hat is going to tell us all values taken by p hat, right? The values taken by p hat in all samples of the same size from the same population. It's the same definition as the sampling distribution of x bar. I change my parameter, what I want to know about the population, so I need to change my statistic, what I'm going to calculate from my sample to use to estimate it. All right? Now, I am on the bottom of page 518 in your book. If we choose an SRS of size n, this chapter here, we still need that simple random sample. We're still taking samples of size n. It says, let p hat be the sample proportion of successes. I already showed you how you're going to calculate p hat on the previous page. P hat is always the number of successes in your sample divided by your sample size. That's how you calculate it. And then it says the following. Number one, the mean. You remember I subscripted the mean with x bar before when we were talking about the sampling distribution of x bar? You're not looking at that one. You're looking at the sampling distribution of p hat. It's exactly p. What I told you before is this. Got to change colors. That's the sampling distribution of x bar on the right there in blue. I also know this, that the standard deviation of p hat is the square root of 1 minus p over n. What I told you before was Standard deviation of x bar is sigma over the square root of n. Then it says, as the sample size increases, the sampling distribution of p hat becomes approximately normal. Of course. It had to be. As n increases, I know I'm out of time. Give me 1 second. The sampling distribution of p hat is approximately normal. So, folks, we have a new normal distribution. We know its mean. We know its standard deviation. That means we can do confidence intervals. We can do tests of significance. We're going to repeat ourselves all in one chapter, except instead of x bar, it's p hat. Okay? We will pick up there on Tuesday. You're going to see me say same things you heard me say before. You're going to see me do here's the formula for the confidence interval. Here's how you do the test of significance. And we're actually going to choose a sample size here also like we did before. All right? Everybody be careful going to the house. We'll see you on Tuesday. Don't forget my homework problems on Tuesday.